team, we have a talk by our speaker. Here we are. Are we on the same? We are on the same link, I guess.
Yes.
Paula's here. Hi.
Yeah. I think
I'm going to very briefly share a slide, if that's okay, just to introduce Paula. Paula, thank you for joining us. I don't know if you had a chance to catch any of that. You will surely have heard that were a lot of questions around methodological issues, statistical sample sizes, how should we validate properly. So we're absolutely delighted to have you with us, Paula. Thank you so much for joining. Paula is a researcher at the Oxford BRC at the Center for Statistics and Medicine. She's a member of the Equator Network, which you should all be aware of. Equator produces guidelines and reporting standards for ensuring that the research we do is transparently and properly reported. She also sits on the Tripod group, which again creates reporting guidelines, and in that case particularly for prediction and modeling studies, which is so relevant to all the things that we've been talking. Apart from her work on developing reporting guidelines and methodological guidelines, she really is an expert in prognostic prediction modeling studies. And I know that you've been working with Fergus as well on how we can use machine learning in oncology, and also to thank you, Paul, actually, for your tremendous work in the systematic review of COVID-19, which has been of direct clinical benefit to us on the hospital side of the community. So, Paula, I won't take any more of the time of your talk by introducing you. Thank you so much for joining, and we really look forward to hearing your keynote lecture. Thank you.
Thank you, Aris, and thank you everyone for joining me today and inviting me to this conference. I have had the opportunity to listen in on the discussion just now, and hopefully I'll be touching on a lot of that in my talk. I might need a little bit of help just because I'm working off one screen and I need to share it. So just bear with me one moment. It's just when I go to presentation mode, it seems to take Zoom away. Is there, I'm just trying to, let's see.
Paula, I can see it starting and it's opening now.
Okay, and it should go into presentation mode. Is that, can you see?
Perfect, perfect.
And can you still just see the slide? Because I don't know if that changed anything.
No, that did not change. So there was no advance.
And no notes or anything.
No notes, nothing else.
Okay, perfect. Thank you very much.
Do you want to just quickly advance your slide one slide forward and back just to make sure? Yes, perfect. Thank you, Paula.
Okay, excellent. Thank you very much for that, Aris. So thank you for this opportunity again. I'm going to talk to you now a little bit about study design, sample size calculations, and methods of evaluating AI models. So the objectives of this talk really are, talk a little bit about the motivation for this, why I'm going to spend the next 45-50 minutes talking to you about validating your models. And then I'm going to go into what we should be considering really when we are designing, through sample size calculations, when we are actually analyzing this data. And then there's some additional considerations really for when we're working with images, which I thought would be quite applicable to this group. I'll then move into talking a little bit more about reporting and the guidance that's, to be honest, is coming. It's not as available as possible, but we are trying to catch up with that. And I'll finish with some closing thoughts. So just as a few notes, I guess, that I'll be focusing on, as I say, image-based models just because of the group. And there is a lot of overlap with the models used in low and high dimensional data like imaging. So a lot of what I'm discussing is going to be relevant to both, supervised models, unsupervised models, low dimensional data, prediction models, high dimensional as well. And also equally, if we are developing for prognosis compared to diagnosis as well. So I think a lot of what I have to say is it's somewhat, a general framework that I'm presenting, which you'll find hopefully useful in whatever type of study that you're doing. So just starting off with a little bit of motivation, I don't really feel like I need to say this, but it's always helpful. But that artificial intelligence, is, and machine learning and deep learning are all advancing. Doing a very quick kind of search in PubMed for publications that are now available that are using terms such as artificial intelligence and deep learning and imaging specifically, we can actually see that actually just comparing, where we are now, 2021, there are twice the number of studies published compared to just a few years ago. So, that's not surprising. There is definitely, increased opportunity, and there's advancement for prediction using medical images, using AI as well in prediction. We see this, a lot of this is actually coming now into the public domain. Just looking at the UK kind of NICE kind of committee, our national framework that we have, it's reviewing support of AI-powered heart flow analysis. We're looking at in cancer, especially, UK has rolled out AI-based cancer detection for NHS patients. Got how AI is helping lung cancer patients in the COVID era. Even looking internationally, medical imaging is innovating, all markets all over the world. It's classifying colorectal polyps, example, it's coming. We're seeing it more and more in the public domain. However, it doesn't come without its problems, and it does beg the question of, is it hope or is it hype? So just to go through, there's quite a few systematic reviews that have been done now, looking at artificial intelligence, whether it's comparing it to clinicians, but ultimately reviewing the prediction models that are now coming available to us, both in the literature and, as I say, in the public domain as well. So this study actually found that there were very few prospective studies in medical imaging. The non-randomized trials that are available were also not prospective. They were found to be at high risk of bias, and they are deviating from the existing reporting standards. And for me personally, I actually think the biggest problem is that the data in the code is actually not available. People are not specifying it in their main manuscript, what actual model they've developed, and they're not making it available for others to then go away and validate. This study concluded that future studies should diminish risk of bias, enhance real-world clinical relevance, improve reporting transparency, and appropriately temper conclusions. And this study is not in isolation. We have another systematic review, looking at the diagnostic accuracy of deep learning in medical imaging. This study found, that again, high heterogeneity between studies, varying methods, varying terminology, varying outcome measures as well. And again, kind of pointing towards the need for, developing reporting guidelines, methodological guidance around the key issues in this field. Obviously, highlighting what we have at the minute is not up to scratch. So another one, looking at systematic review, this time looking in radiological cancer diagnosis. Again, finding very similar findings, frequent omission of clinical information, including eligibility criteria, really basic kind of information we expect to see. Less than 50% of these imaging studies assess model performance on explicitly unobserved test data. If you link that back to the first systematic review, which is highlighting the lack of code and availability of the model, this was also kind of unsurprising. And then, it concludes design and reporting standards have improved in, neural network research, but many opportunities still remain for further progress. Here's another one, it's looking at the role of AI in real life clinical practice. Again, another systematic review. And again, just kind of indicating that, there is, AI in some respect is still at its early stages, and there is, great potential there. But more research is needed. We are kind of up against benefits, but also, we're up against those challenges as well associated with AI applications, which I think, having heard the discussion earlier, you're more than aware of. So, there is this building body of evidence, to temper the inflated claims of AI, and it just begs the question, is there some unlocked potential still there? I think we see this potential and AI almost used interchangeably together all the time. So it does beg this question, are we in this space that, still there's unlocked potential here, given all the challenges that. Just looking very quickly as well at this Gartner hype cycle, and I think this is really quite depicting quite nicely where we are, where we've been, where we are, and where we're going with AI in general and prediction modeling as well. I think looking at those systematic reviews, I think we can all agree that we're probably sitting around that we're still battling those peak of the inflated expectations. There's some disillusionment. We're knowing there's challenges, there are problems. And I think the guidance, is going to bring us out of that. And I think this is where we're currently sitting. Because many models are being developed, they're not being validated, various problems with that. And the basically, ultimately, they're contributing to a lot of research waste. And, imaging, where AI is a lot more justified, because there's arguments that have occurred in terms of whether AI is more or less useful in lower dimensional data. It seems to work better with high dimensional, such as imaging. But as I say, it's not without its problems. So how do we try and remedy this? How do we get around it? Well, it's the studies, we want to be looking at, we want to be conducting as well. And what do we need to think about in terms of the study design features if we are evaluating these AI models? So at the research pathway for a prediction model, we start by the development, involves some sort of training, there's some hyperparameter tuning, and there's testing, internal testing as well. We move on, we can then externally validate the model where we're really testing the model on new data, brand new data, unlinked completely to the development data set. And then all being well, and again, just kind of reflecting discussions this morning, we can then lead into the effectiveness where we're implementation of the model, in clinical practice, where we then need to be testing the effectiveness of that model in clinical practice. And as I say, the talk that I'll be going through today and focusing on is really the external validation. So we're after the development stage, the model's been developed, but we are before the release of the model, let's say, in clinical practice. So with external validation, or just validation in general, I think what I've come across, especially around reporting and conduct with the reviews that I've done, is that there's a real confusion with what is internal validation and how external validation is separate from that. Because both in essence are evaluating, it's evaluating the model. But with internal validation, the kind of aims, and this is what we need to remember with everything we're doing with our studies, what kind of platform are we coming from when we want to evaluate the model? So with internal validation, we're interested in looking at the accuracy of the model, so the robustness of our estimates of those coefficients that we've estimated for our prediction model, and account for any kind of optimism possibly in the model based on the data. We'll probably review the modeling approach. We want to know how those variable selection procedures have occurred, and we want to look at the robustness of the model as well. The important thing to remember is that this happens as part of the development process of the prediction model. It's not separate, it is definitely within that, and it can be considered very much embedded within the development process. So comparing that then to external validation, we're looking at more the generalizability of the model. So, is the model performance in a similar or different populations to the development? So we want to assess the model performance, how well it's predicting, either in a similar population or in a completely different one to that it's been developed in. So it doesn't use any of the development data. And the key thing that I really want to point out here is that a random split sample is not external validation. I've come across this time and time again, where and I think partly it seems to have caused kind of this overinflation of conclusions from prediction modeling studies and their performance, is that to a degree can be based on unseen data. People seem to then liken it to external validation, which it isn't, because we've split the development data. It's still very much part of the development process. So where we see then, these kind of analysis flows where we have a data set, it's then split, we can train it, we tune it on part of the data, we test it on the other part. This is not external validation. Again, when we're splitting it, we've got a training set, a tuning set, not external validation. It's part of the evaluation of the model, but not external validation here. And I think it's important to make this kind of distinguishment between both, because your internal validation is still, as I say, it's based on your development data, so likely the performance is still going to be that slightly bit higher than what you would expect in a separate population, which is fair, which is fine. And again, we should be reporting it like this, and we should be, as I say, highlighting the context at which these performance measures are coming from. So, types of external validation then, it varies from our aims, depends what we want to do with the model, whether I want to take a prediction model from a completely different country and I want to see if it works in my clinic, or in a different group of patients, whether it be that I want data, I'm thinking about updating the model. And so possibly I then need a different time period. So these are basically, the things that are varying when we are externally validating. We could either have a different setting or population, different geographical location, which again could link to a different population as well, or a different time period. But with imaging as well, we've got this added layer that we could actually also be trying to validate our model on different, image capturing devices, for example, different settings. They will all have an effect on the model performance. And it's really, as I say, it depends on our aim, what our interest is, as to which one of these we then want to pursue. In terms of then how that plays out in terms of a study design, we could be having a temporal validation. Again, we're varying the time periods. Maybe I want to develop it on 2 years of data in 2010 to 2012. Then perhaps 2016 to 2018, I want to do an external validation. Does it still work as well as it did back then? Got geographical, I'm varying the location, as I say. Is it that it's the same time period, but perhaps it's a different center, it's a different country, it's different population, it's a different sample of patients, basically. We could also have independent validations. In this case, it can be temporally different, so it's a different time period. It's also a different as well. But most likely, it's either the same or a very similar, research team that's conducting that validation, external validation. Or it could be fully independent. We could be changing the time period, changing the geographic location, and it's a whole different, group of researchers, a truly independent, external validation of an existing model, which is also incredibly useful. And all of this, one of these to a degree, possibly actually going up to a fully independent is possibly needed before we're even considering the release of a model into clinical practice to just show the robustness of its performance. So just a very quick example here, and I'll be referring to this example in addition to another one throughout the talk. It's looking at an artificial intelligence assisted prediction of preeclampsia. It's a development and external validation. So they are developing a model and they are externally validating in the same data set. In this instance, they've used a nested case control, which I'll talk about in a short while, as to what's good and bad about this in terms of the study designs that we use. But in essence, they state that they split up their tidy data set into training and test sets for internal and external validation. So they are being quite explicit. Likely it's an independent validation because obviously it's in the same paper, it's the same study team, but actually going a little bit further into their manuscript, you can actually see what they've done is that they've partitioned their data sets. They've done an external validation, split geographically and temporally, so they've done two. And then, they say that they randomly sampled one city in each province, and for the temporal split, they've done 25% of the days. So, I mean, I could go into a bit of a rant as to what they've done, how they've done it, and whether it makes sense to me. But I mean, the point really here is, just to illustrate the different types of validation. Here, they've actually done two. I could question their methods to a degree, and whether it is a truly, geographical and temporal split, or whether they seem to be somewhat have randomly sampled something. So there are some issues there. But point being, they've done two. This is what we would hope to see, and we would want to see reported. Another example here is looking at TB. So can artificial intelligence be used to accurately detect TB from chest X-rays? And this one is a fully independent external validation of 5 different models. So they've taken 5 existing models, they've applied it to their data set, which is based in Bangladesh, and a whole new study team. and they've just gone away and see, well, how these 5 work in their data, basically. So these are the different types of external validations that we tend to see. It is important to note, and Fergus actually mentioned this in the panel talk as well, that, you know, there is a changing case mix over time. You know, there will be some differences that occur. There will be improved techniques, there will be improved surgeries, and etc. And so it's just worthwhile bearing that in mind. And this is why it's so important to be really quite descriptive of your patient sample in any external validation that you do, because it, again, puts in context, you know, any change in performance and, you know, just the performance that you get, basically. Equally, if you're looking at changing case mix between centers, so even if you're doing a geographical, you know, external validation, likely there could be some improved, or perhaps even worse in clinical protocols, which are, you know, leading to improved outcomes, but again, may affect the performance of your models that you're validating. So, as I say, really important to be reporting that case mix. You know, who's in your sample, how does that differ from the development data set? Really important with putting that model performance into context. So, I mean, I think this also came up in the panel talk as well. There's a lot of talk about, you know, doing an RCT, you know, or how and when we do that, basically. But what I would say is that when we are validating a model, really what we're looking for is a cohort study, prospective cohort study, ideally, or a cross-sectional kind of data set if you are looking at diagnosis. If we were comparing models, again, likely you'll see that and you'll want to see the performance in a cohort study if it's a prognostic model, and a cross-sectional study if it's diagnostic. And it's only really when we are looking to evaluate the effectiveness of the model where we then want to be thinking about a more interventional study, whether that be an RCT, but they can be quite difficult, quite long, and timely, and in essence costly to do, given the nature of the study. It's not a drug, it's a model, it's slightly more complicated. And so that's just worth bearing in mind. That's really where we want to be seeing the kind of interventional studies. Where we are at the minute, we're validating still. So as I say here, you know, we're looking for a nice prospective cohort study or a cross-sectional study for validation, external validation. And yeah, ideally, we really do want prospective data, especially when it comes to external validation. So it's not just the data collection, but also any image annotation as well. You know, if we can have that as prospective, it really does help with the integrity in the study. You know, what the prospective data, you know, you actually designing a study, you going out and collecting that data yourself, you know, if that's researcher-led data collection, it gives you full control as to what you're getting. It's reducing, in essence, hopefully that risk of bias, any potential risk of bias in your study, as well as if you were to, for example, if you're using retrospective data, existing data, which has already been collected, we have less control over how things are collected, whereas moving forward, we do have a lot more control and we can build in a much stronger study design. The longitudinal component is important for prognosis, but we do actually need to be careful when it comes to diagnosis, and that we're not actually letting too big of a time period elapse between, you know, the image acquisition to, you know, finding out the ground truth, perhaps. So the interval between the image ascertainment and the gold standard outcome, if that goes on for too long, we're including too much time, that can also cause problems. But I'd say that's more related to the diagnosis of a diagnostic prediction model, sorry. So quickly, just looking at an example, we've got the TB study, which we saw earlier, stating that, you know, they say it's a retrospective study, you know, but then in the actual paper, they say, you know, individuals greater than 15 presenting to 3 TB screening centers in Dhaka, Bangladesh were recruited. I mean, they have stated that they're using retrospective, but talking in terms of kind of recruitment and consecutive recruitment, it pushes me to think that actually likely it's more of a prospective study here. So it's really important that we get really clear as to what we are doing, where our data is coming from, and that we are describing it appropriately in our manuscripts, leaving nothing ambiguous in any way, like this study has done. So I'm now clueless, which I imagine a few of you are as well, as to what exactly has been done. But, you know, we want to be reporting that as well, being really clear as to where our patients are coming from. Blinding is actually another really important study design feature, which especially matters for imaging studies. So, predictor or image assessment, it can be influenced if assessors are not blinded, especially, if you're getting radiologists that are assessing and annotating, the images. We ideally would want them blinded. And again, if we're doing this prospective researcher-led study, that's more like we have more control over that. Because the knowledge of the outcome can contaminate that predictor and image assessment. And, it's a particular issue for these imaging studies and diagnosis studies, just because of the subjective and the small time intervals that can artificially of some associations as well. So it's just worth bearing in mind, both for development and also for external validation. Going back to the TB study, quite nicely, they blinded their radiologists to any information except age and gender, and they were reading 15 to 20 x-rays per day. They also state that the 5 AI algorithms scored were anonymized, images were retrospectively and independently and blinded to all information. So that's really important. We want to be ensuring that, whether it be development or validation, that we do talk about blinding. And as I say, it's especially important for diagnosis and imaging studies. And why is that? So, the issue is that likely for some areas, this issue of ground truth. Now, we need to be checking for outcome definitions used for development here as well, and make sure that, again, if it is something different in the external validation that is explicitly reported in the manuscript, ideally we want our outcomes to be objective, but it is challenging clinically, and we do need to appreciate those limitations. And often, we'll get 2 or 3 radiologists that will annotate the. Can we call that ground truth? I'm not too sure. So, it's basically what we end up doing then, if we have the radiologists kind of becoming the gold standard, or creating that outcome that we want to be comparing the model to. And in some respect, what we're doing is we're comparing what a model thinks and what is it it's estimating is disease to what humans is in essence doing the same thing. So, and again, we touched on this, it was touched on earlier in the panel discussion. That's where the inter-rater agreement becomes very important, that we can kind of look at that between the radiologists and, be slightly more certain in the ground truth. But again, because this has such a big role in both development and also the external validation, any study design using imaging, something that should be very explicitly reported, and it definitely should be considered as well. The inter-rater agreement should be considered as part of the study design as well. And if a biopsy is needed, ultimately, and especially I guess for cancer-based studies, annotations will be insufficient if a biopsy is needed. If we can get it, that is the ideal. I saw this kind of hierarchy of data annotation, which was quite nice. Says it, increases value kind of goes up with, we start with retrospective annotation. So this is then linking to those retrospective studies possibly that we're using, existing data we don't have, compared to, building off of that prospective annotation, definitely better, increases in value. You're recruiting patients and you're evaluating it. Just brings a whole kind of better infrastructure to your study, and that takes care of a little bit of blinding as well through the prospective annotation. And then sitting on all of that, if we can get something, true ground truth through a biopsy, for example, all the better. And those comparisons are then more robust as well. So, differing outcomes can introduce a lot of heterogeneity. There's possible measurement error as well into your study. Again, the importance of highlighting that inter-rater agreement and also being very explicit in your reporting. Note also needs to be taken on the machine that's producing the image, possibly the thickness of the slice, the section of the image, any other kind of settings, because, ultimately what you're feeding, the image that you're feeding the AI algorithm is, that's what it's going to use, that's what it's going to evaluate. Also, you could think that actually is that exact same image, is that's what's being presented to the radiologist, or is they getting, the whole image? I don't know, where they can possibly see more, I don't know. So again, we need to just be mindful of these features. So just looking here that, which part of this, image is shown, to the AI algorithm or the radiologist, it will come with different, varying kind of results on this. So as I say, want to be quite mindful. And I think another thing that is incredibly useful to be reporting quite explicitly are the data pre-processing techniques as well, which is ultimately, defining what then is fed into the image. So that's a little bit about, kind of more the specific areas for features when it comes to, external validation studies for AI imaging. Now, this has come up quite a few times. So sample size. So I'm guessing a lot of people are ready to kind of hear something about this, I guess. It's recognized as one of the biggest influences for development. There's a lot of literature out there, but what about validation? Sadly to say, it's often overlooked. And what those systematic reviews and my own systematic review in this area has found is that there is a very high variation in the sample size studies that's used. There was one systematic review that found there was a mean of around 2,000 patients informing the external validation for studies, but looking at the range, that ranged from anywhere from 100 all the way up to 7,800. In my own study, I did a systematic review of machine learning prediction models in oncology. It wasn't imaging, albeit that's fine. But what I found was, again, a median of 553, but that range, anywhere from 11 patients all the way up to, 800,360, 6,659, It's really high variation that we're seeing, and that's what really is the problem here. And then looking at that, and the median number of events that are forming it, arguably this is what actually we want to be using when we're informing our sample size calculation. 50 patients with a range of anywhere from 7 patients to about 1,300 informing these analyses. And this is a problem, as I say, probably not the absolute number, but the variation is a really big problem in this area. And so guidance is definitely needed. So what do we want here? So now when we're developing a prediction model, our aim is to robustly estimate those coefficients for the prediction model. When it comes to external validation, we're less interested about the estimation of the coefficients because we already have them. What we're interested in here is the estimation of the model performance measures. And that's the key thing here. That's what we need to remember. That's what we need to power our study for, our external validation for. So we want to have enough to ensure reliable estimation of those model performance measures. Recommendations that are out there more generally for prediction, less specific to AI, there's an argument to be made that actually it's still relevant because as I say, we're less interested about the development, we're interested about the model performance, and that's relevant for all studies, whether you're doing an AI model, whether you're using imaging, whether you're using clinical characteristics, low dimensional data, doesn't matter. So I think this is very relevant. And the guidance that is available for one can also be used for the other. So recommendations are to have a data set with at least 100 outcomes. So this is somewhat of a rule of thumb. But you need to remember that when it comes to prediction, the sample size that we're interested in is not so much the total sample size, but it's the number of events that we have. And making sure we have enough number of events to allow us for, as I say, for that estimation of the coefficients in development, but for that estimation of the model performance in external validation. So if we have a 1% outcome prevalence, then we're going to need around 10,000 participants in our external validation. As that increases, the number obviously decreases as well. Very much a rule of thumb come from various studies over the last 10, 15 years. We've got one study suggesting 100 events, 100 non-events. There was another study saying a minimum of 100 events and ideally 200 events or more. As I say, these are the number combined with the prevalence of your outcome. Obviously, that will be an increment. But this has come a little bit outdated. There's been further studies adding to this. So we've got the external validation, clinical prediction models. They've done simulation kind of sample size calculations where they found that was more reliable than the rules of thumb. So we really are trying to push away from any rules of thumb when it comes to sample size calculations. And quite nicely, and very recently, I have to say, there's been these 2 very nice studies that have come out through, which is basically looking at calculating the minimum sample size for external validation of a clinical prediction model with continuous outcomes and binary outcomes as well. So this is now available to us, a very, very rich source of information when it comes to sample size in this area, with code available in the appendix as well. So I can't recommend these highly enough. I've used them myself and find them very, very kind of beneficial to use, just to know that we are informing our studies appropriately. As I say, the criteria for both of these really are based on, the precision of our model performance estimates, looking at the outcome proportion that we need, any kind of miscalibration, which we need to account for, and some potential risk thresholds as well. And this is suitable if we are doing something more researcher-led or prospective data collection, existing data set as well, just giving us an indication of that we do have enough or that we don't have enough, then we can work with that, we can amend, but we should be doing this at the protocol stage. So where things are definitely a little bit more flexible. Now, in terms of, as I say, model performance estimation, we've kind of got some key offenders here. We've got discrimination, looking at area under the curve, under the ROC curve. We've got calibration. We're looking at, the accuracy of our estimates, the slope and the intercept. And we're also now getting into the realms of clinical utility based on possibly a decision curve analysis. Now, we may be estimating one, some, or all of these in your sample size calculation. And as I say, those papers will allow you to do that. And what, in essence, you want to do is calculate it for each of the measures, and then obviously take the maximum, which becomes the minimum for your study. So let's use the, tuberculosis example here. So they had about 24,000 individuals, including the analysis. They had about 3,600, highly suggestive of TB. So they've got an event rate of about 15%, but they do state in their paper that that's higher than their national average. Okay, so let's assume a prevalence of about 10%. I'm just doing this for purely just example. This is by no means accurate. But they are externally validating 5 models. And so what I did, I went through and I basically, we would get this information from the development study. I've picked it out from their external validation study, absolutely fine, just for illustration here. But they've got 5 different models. They have varying kind of AUC values, but in essence, it's a range from 0.85 and 0.91. Now, what I've then done is used that sample size paper, and I've estimated based on if I would want to then go away and conduct an external validation for these 5 models, based on this range, I'm going to require a minimum of 644 patients with 65 events, and patients to accurately estimate the AUC for every single one of those models. So this is what we would expect to see. So if you're looking at multiple kind of prediction models, you would want to run it for each one of those, the expected kind of C statistic or the AUC for each of those models. You would then want to take, as I say, the maximum that's required, and that would, as I say, informs then becomes your minimum that you then need. So you would repeat it for then all the other measures that you're interested in, that you can, because a lot of this does based on the availability of information in the development study, which hopefully you might all agree with, but it is lacking. We've seen it in the initial studies, in the systematic reviews, that there is definitely kind of a lack of information there. So it can be a little bit challenging. We have to make assumptions, but where we can, we want to be doing the sample size calculations based on those estimates. So really, if there's one thing I want you to take away from this part is that, it's based on the estimation of the performance measures. Firstly, that's where it differs from a development study. Secondly, we are going to probably be looking at multiple scenarios, multiple models, multiple scenarios, multiple performance measures. And we want to really be mindful that we are looking at each of those and looking at the amount that is needed for all of those. And then, as I say, taking the maximum, which then becomes our minimum for our external validation study. Now, when it comes to imaging, though, this is the other thing that I come across often is, well, are we talking about patients or images? Because there are many studies that I see that they will say, look, we had 50 patients, but we had 100 images. Okay, fine. Often there is more than one image per patient, and then we go even further. Is there more than one nodule per slice, or per slice per image as well? So again, it's something that there's no real kind of hard answer for this. I think for me personally, I would always go, for the patient level, just because then I know I will be adequately kind of, powered in some respect for again, all scenarios, because that will be our maximum. And then we know if it is multiple images, then we have that. But the main thing we want to do is ensure that all levels are reported within our patient level characteristics. That's the most important thing. Again, there's a review that I've been a part of that's yet to be published that was looking at diagnosis of lung cancer based on imaging. What we found were people reporting patient level, well, just the number of patients, but then weren't reporting the number of nodules when that was informing the actual algorithm with the nodules or the images. Or that they would tell me that they had 10,000 images, but didn't tell me the number of patients. We need to be really clear of all levels of information here. And as I say, as a bare minimum, we want to be reporting the patient level, because we need to know, we get so much out of the patient level characteristics. We get to know the context of the study and that baseline sample as well. As I say, the guidance that we have is currently at the patient level. And as I say, just out of experience, when through systematic reviews, when we are evaluating these studies, it's also at the reporting at the patient level as well. So, that's the sample size. And then, we can go on and then start thinking about analysis. We get the data, and try and evaluate our model. So what makes a good model, let's say? We want something that ultimately is accurate, clinically is credible, generalizable to applicable settings, shown to improve decision making. But how do we know? How do we know this? How do we then take those measures, and how do we kind of build off of that? We want to be looking at calibration, want to be looking at discrimination, we want to be looking at clinical utility. As I say, key offenders, informing sample size, only right, they're going to be coming out of our analysis as well. This is all in context of the aim and the setting. We do have classification measures as well, which is very popular, especially when it comes to diagnostic models, where they are probably more applicable in the diagnostic setting than prognosis. So we do need to be careful, because ultimately what we're doing here is we're introducing a threshold. We're possibly dichotomizing a continuous risk that is given by the output of the model, and more relevant for the diagnostic models, but we want to ultimately make sure we're using them to support the main performance measures, those three. And just to be aware that there is often a loss of information. So if we are introducing a threshold, make sure it is clinically informed at the very least. So when it comes to model performance, we've got discrimination, which is looking at the ability of the model to separate events from non-events, presented with the ROC curve. Essence, it's telling me that in a discordant pair of patients, that our prediction model, our AI model, is assigning a higher risk to the person who actually has the event, and a lower risk, possibly, than the person with lower risk, or that doesn't have the event. That's in essence what we're seeing. When it comes to calibration, we're looking at the agreement between the observed outcome and the predicted probability. So if we're predicting, a 20% risk of transfusion, let's say, or of another clinical outcome, the observed frequency of this in our data set should also be around 20%. But the calibration part is really interesting, because it tells us a lot about how our model is performing over the different risk thresholds potentially. And it can tell us that, where our model potentially is underestimating risk or overestimating as well, which is actually really valuable information. And then we have, the decision curve analysis, as we said. So this gives us some insight into clinical consequences. It provides a net benefit from using the model over a range of clinical thresholds as well. So if we are introducing a threshold, possibly we need to be looking at it at multiple thresholds as well. And the nice thing about this is you can see the clinical consequences of that. Just to circle back here, though, to the importance of calibration, though, because I often, as I say, with all the systematic reviews and the outcomes of the reviews that I've presented, it's often overlooked, it's rarely reported, but it's just as important, if not more important, than the discrimination. Because as I say, you're getting a lot of information as to where the model is, accurate or less accurate, where it's overestimating or underestimating, and ultimately that is what is informing your clinical decision making. And it's linked to the outcome prevalence, tells us about the accuracy of the predicted probability, as I say. So this is something we want the discrimination and the calibration to be reported together at the very least. So just looking at the preeclampsia, they quite nicely presented this table. So we've got calibration measures, we've got discrimination measures as well. It's quite a heavy table. They've obviously done it by internal validation, external validation, the geographical split, external validation, the temporal split. And ideally, what we want is to see that the calibration, the slope, is as close to 1 as possible, and the intercept to be close to 0 as possible. So that would be the perfect calibration, basically. But what we can see, so if we just focus on the geographical split or the temporal split, what we can see is that there is some miscalibration. A lot of these are off 1, a lot of them are off 0 as well. The intercepts are off 0. But it really highlights that we really should not be relying on a single measure, really, but rely on discrimination alone or calibration alone for that matter. Because if we see here, we've got, say, for example, this ensemble model, it's got quite high, there's some miscalibration here, quite high miscalibration. But if you look at the discrimination, we've got 0.72, which I think some people, if I were to present that in isolation, would look okay, actually, the model's going well, but actually it's miscalibrated. Overestimating somewhere is underestimating somewhere. Equally, if I choose this model here, it's an artificial neural network. It's got pretty good, a pretty good slope. So lower, lower miscalibration overall. It's got a better intercept, closer to 1. But actually, looking at the discrimination here is 0.58, so lower basically. So point being, when we're presenting, we want to be presenting all of this together, we want to be reporting it all together, just so we can make a better informed decision, because it's not just the discrimination that matters, it's calibration as well, and potentially other measures, like the decision curve analysis as well. We want to create a body of evidence with these studies, not just a single estimate. And we want to be putting these findings into context. So I mentioned case mix before, and that's really the sample of patients and possibly what their clinical characteristics are, how that differs possibly from the development study. And so it's really important to describe those differences in the development and the validation data sets, whether it be study design, whether it be imaging protocols, whether it be images themselves or the analysis, and also, as I say, the patient characteristics. We want to be describing a sample, we want to compare what the model was developed on, provides that really important context for the performance of your model in the external validation. But however, it's very rarely reported in imaging studies that we found. Very quickly here, so we've got the TB example, we've got same, patients, 24,000, got 15% event rate, and it says it's higher than the national average. So when we look at then the kind of the output of those models and how they perform, that's then informative. So we can then put those measures, those changes in performance, whether it drops, whether it increases, we can try and then figure something out here, see where it's working, because ultimately then we can be a bit more kind of directive as to where we put that model. Is just, again, they compared the 5 models. One was from the Netherlands, you've got China, South Korea, another from India, and they're validating it in Bangladesh. So as I say, really important to see those differences. And then, explain any of those differences. So possible sources of heterogeneity. So, imaging studies often need to include description of those additional factors as well for consideration. So data pre-processing methods, what exactly is the AI model seeing? What is the radiologist seeing potentially? What section of the image, what thickness of the image, and what imaging machine may be, including those settings. Another thing that we often see is that we want to compare these models, whether it be to other models or humans. And what we need to do is make sure, at the very least, that we've designed the study to allow us to make that comparison, and that those comparisons are fair as possible. So want to be kind of, comparing the performance measures, possibly you can consider a decision curve analysis as well. But basically we want to be making sure that, if you've developed a model, make sure then that external validation is an external validation for your model, as well as any kind of existing model you've compared it to. Otherwise, it's, in essence, it's unfair. There was a lot of chat about this morning in terms of actually comparing to humans. So, can you actually compare, there's this issue about ground truth, estimation versus estimation, and again, we need to be quite careful when we are conducting and designing these studies. There's no real hard answer. I think it very much depends on individual kind of settings. We want to ensure ultimately, though, that the study is designed to allow you to fairly compare, whether it be humans or whether it be to models. So example here, we've got the TB, they first compared the performance of the group of 3 Bangladeshi radiologists with 5 AI algorithms. So they're comparing humans to their models. And they state that all 5 AI products significantly outperform the radiologists. this is not a statement, that we rarely see. This is something that occurs over and over again. And I don't really get it personally. I don't know why we want to beat humans for some reason, but anyway. But looking in their study, they say that they've got 3 radiologists. The radiologists graded the X-rays normal, abnormal, and they further kind of classified, the highly suggestive. So they classified the outcome. So it just begs to then question, is this actually a fair conclusion? Is it justified? Is it even possible? So it's just bearing that in mind, whether we're reading these studies, whether we're conducting them, as I say, make sure they are designed for purpose, basically. So now, I've touched on reporting and guidance quite a lot just during my talk, but I just wanted to just kind of sum up a little. Reporting is poor. We've seen it. It was the, sort of at the start of the talk, there's a lot of heterogeneity. The issues seem to be, there's low availability of the models. There's no description of the development or validation data sets. There's no description of patient characteristics, which I think is probably one of the key things that really, is a real issue that could be so easily solved. And, findings are often overemphasized because of that. And another issue that we see constantly is that this terminology is extremely varied. So it can get quite confusing when we are reading what in one study may not be the same meaning as the other. Now, to help this, I know it seems like a lot of you are aware of these already, that, the Tripod initiative has launched, Tripod group has launched the initiative to create Tripod AI, which is in progress right now. It's in the second, we're going into the second Delphi round. And there's also Probast AI, which is also in production, which will help with risk of bias and critical appraisal as well. Here's the protocol if anyone's interested, available on BMJ Open. Starred AI is also in progress as well. Protocol is available again, but again, we're going to be waiting a little bit longer for these to be available to us. There's also the Decide AI tool as well, again in progress as well. New reporting guidelines to bridge the development to implementation gap in clinical AI. In the meantime, though, Starred are still very applicable. We have some additional guidelines as well. I know I heard claim being mentioned. My understanding is, though, however, with claim, it may be useful for now. It hasn't been that robustly developed. There's been no real consensus and Delphi involved in that. So just be a bit wary with some of what is available to us. And look how they've been developed as well. Essential reporting items for prediction in general are still going to be applicable for AI studies, for imaging studies. If anything, we'll just add a couple more items. We're not really going to be thinking to omit anything. And there's a real need to push towards that transparency, namely in imaging and ground truth details as well. And as this guidance is being developed, improved reporting is a bare minimum that we can do right now to help the situation. So clearer definitions, clearer analysis, clearer descriptions of patients, clearer benchmarks, clearer context overall, especially for comparisons. So just finally, some closing thoughts. I presented our Gartner hype cycle here. I think we're still sitting around here, but to get to that plateau of productivity, we need those reporting guidelines. We need the methodological guidance and expertise in the studies, and probably most importantly, we need those tempered expectations as well as to what we're doing. As I say, just appreciate that we are in the early stage. That's an exciting point. And arguably, yes, there is unlocked potential with AI still, but arguably the real unlocked potential is the potential of a well-conducted, well-reported study where conclusions are justified and as true as they can be. Or, those studies will be the key at the very least for AI. Thank you for your time. I believe we've gone over a little bit. I apologize for that, but any questions?
Oh, Paula, thank you so much. What a fantastic overview of so many of the issues that we've been talking about, and so many of the questions that we've been grappling with as well. Really, really brilliant. We've just got a few minutes for a few questions. There was one question that, again, about sample size, not surprisingly, really. In terms of validation sample size, but what about developing models? What guidance do we have about, we go to the ethics committee, we say we want to develop a model. We don't really have such a strong knowledge in advance of how much data our data scientists might require to build these models. How can we best estimate that? Should we be doing pilot studies? Should we be basing it on? What's your advice there?
So by the same group, so I've presented the two validation sample size papers. There are two really nice development sample size papers by Richard Riley et al. I can post the link into the chat after we're finished to both those papers, which are extremely useful. And the best thing about them is that they have also made the code available. So they are actual kind of statistical packages that you can download in R, in Stata, and you can run those sample size calculations. Now, what they need, as I say, because we're evaluating at that point, we're estimating the coefficients for the model. So what we're then looking at, we need the kind of anticipated C statistic again. It's the outcome prevalence rate, and it's also the number of parameters that we're interested in, and that's overall, not just the ones that enter the final model. So I can't push you in the direction of those two papers enough, to be honest, because I think that will help. They are formal sample size guidance. There's a lot of research gone in behind them as to, and they are closed form as well. So there's some formulae there. As I say, yeah, I think I would leave it there. I don't think I could really add more to those. But other than the fact they are incredibly useful, we do have that available, and I would push for any researcher to be including that calculation in any kind of study they then want to design, basically. Yeah, that would be the way.
Thank you, Paula, and for the delegates on our call who've been thinking about that, and we have with us data scientists, computer vision experts, clinicians, sonographers, radiologists, the whole breadth of people who are involved in maternal and newborn and child health, as well as developing AI models. My advice to them would be, please ensure that you check the latest reporting guidelines and take advantage of the guidelines. The guidelines aren't there to kind of tell you off or box you in. They actually are really, really helpful to ensure that your output, be it an academic paper or eventually a device or some kind of tool that is to be used, following those guidelines will maximize success, really.
Yeah,
follow
absolutely.
those. And the second is to get statisticians like you involved early as well.
Well, this is it. So when I mean, the final slide, it's not just about the methodological guidance, but having the expertise as part of your team as well. And just making sure you've got the right people involved, just because that will ensure success then moving forward. The guidelines themselves for transparency and reproducibility as well. Yes, they can be used to just inform the study design, at the earlier stages, but I definitely wouldn't rely on that, because ultimately they will tell you what needs to be reported, but in terms of what needs to be done might be slightly different. So
you're absolutely right. So that crucial first step, which is actually designing the study. So you talked, for example, about, actually, do you need a randomized trial? Or are you doing a study of diagnostic accuracy, in which case actually what you probably need is a prospective cohort study that is properly blinded and properly ground truth. So it's so crucial not just to jump ahead and say this is what we're going to do, how are we going to do it. Take a step back and say what is the question in order to design the question the right way.
Absolutely. So I talk a lot and I teach a lot on research design, and that's always what we go to. So what is the aim? We always come back to that. What is the aim? What is it that you want to do? As I say, if it's diagnostic accuracy, you're looking at a cross-sectional study, or if you're looking at effectiveness, that's really when we're delving into RCT. I think the confusion comes in though, in that an RCT is a prospective study, a prospective longitudinal study, which again can be used for development as a data set. You're not running an RCT, you're using a randomized control, an existing data set basically that's come from an RCT, and that could be useful for development, but you're not running your own RCT at this point. I think that comes very much later when it comes to more implementation, when you want to see if the model is actually effective in clinical practice.
Paula, thank you for what has been a fantastic tour de force of all the statistical and methodological issues of AI.